Okay, our next team is team number 16, Powerhouse for National Grid.
Good morning, faculty and fellow students. We are Team 16, National Grid Powerhouse. Our goal of this project is to replicate a small, sustainable house to promote renewable energy. This house will be used by our customer as an educational tool to promote the core values of National Grid. Today, I would like to extend a big thank you to our customer for supporting us every step of the way. And basically, we'll have voltage going through the house, which will be transformed down so it'll be safe, going through resistive loads, and we will have sensors sensing it and then transmitting it to the touchscreen display. Basically, for power, we'll have a two transformer, AC to DC inverter, solar panel. And for software, so for loads, we'll have 5 loads, and for software, why is this off? And for software, we'll have Raspberry Pi and an MCP 3008 for ADC connection. And Abdul will talk about the power.
Hi everyone, my name is Abdul. So my lead role for this project was mainly in hardware, and I was focusing on the power and safety of the house. So we have 2 main power sources, as you guys can see. We have the wall outlet, and we're simply getting power from that wall outlet by using a step-down transformer that will step down the voltage from 120 to about 12 volts AC, and this will power the loads. And then the second power source is going to be our renewables. So we're getting the power mainly from the battery. The battery is charged by the solar panel. So the solar panel charges the battery. The battery powers an inverter, DC to AC inverter. Then we also have a second transformer in there that will step down the voltage and power the loads like the rest of the loads. Since we're dealing with power and like electricity and like a lot of dangerous stuff, I also decided to focus on safety. So on the secondary side of the transformer, I used inline fuses, and we're capping our current in the system in about like 1.5 amps. And we also have a couple of other fuses. We have like another one on the primary side that comes like from the manufacturer, and also like for the inverter there's also like a fuse inside that. But this thing will, like, if in case of like current surge or like any short circuit like things that happen, this will just burn first. So this is about the current capping, and we also have main switches to turn off the whole system. For the wall outlet, we're using like an extension cord because like we had a requirement that the extension cord should be at least 15 feet. And this is our extension cord, and it will have like a main switch that will turn off the wall outlet power. And then we'll have a switch on the inverter that will turn off the power coming from the renewables. And then after that, Rick will explain the rest of the hardware stuff.
Okay, so I also worked on the hardware side of the project, and I'm more engaged in circuit troubleshooting. So I had mainly two tasks. The first one would be to design and create the loads for the system. They involve resistive, capacitive, and inductive. Here in the pictures, they might look somewhat silly to you guys, but they work. So they serve the purpose of simulating real household appliances. I'm also in charge of getting the power factor as close as to 1 in order to minimize the power loss in our system. And the second task for me would be to set up a lighting efficiency comparison system.
So I mainly worked on the sensors not gonna lie, we had multiple failures on sensors that didn't work as well as we wanted due to either noises or unexpected errors. So in the end, I worked closely with my software and other electrical engineer teammates to make a sensor that worked for this project. So on your left we'll have the resistive, capacitive, and inductive loads, which will be powered by the wall outlet, which is safely transformed step down with the transformer as mentioned by my teammate. And on your right side, we'll have the two resistive loads from the battery, which will also be inverted to AC and then safely transformed down. And those two inputs will be measured and go to the MCP and then to our Raspberry Pi to be displayed.
So I was in charge of communicating between Raspberry Pi and ADC chip using SPI and other Raspberry Pi related things like setting it up. And so some of the first few things I did on the Raspberry Pi was set up an Apache web server right on the Pi because we needed a website, and I was thinking of ways we could do it the most easily and efficiently. Originally, we considered like an Amazon web server, but then we would have to deal with internet connectivity issues everywhere that the customer might bring the project. So in the end, we decided it would probably be easier just to host the website, the web server directly on the Pi. So I was mostly in charge of writing the code that communicates from Raspberry Pi to the ADC chip, obtaining the values, doing calculations to get from the 10-bit ADC value, get the voltage values, calculate the current, get power, cost power, and output those values into text files that are easily accessible by the website.
Okay, so I'm Ernie, by the way. Along with helping Z and Jeff with the sensor circuits and SPI, I also was in charge of developing the website interface, which we are using to display all of our data on a touchscreen. There's 3 web pages, one for the power consumption of the house, one showing the average cost of that power, and one for the graph of the power consumption over time. The graph is made using plotly.js. It plots in real time, so while you're switching the loads on and off and the system's all connected, you can see how the graph changes. So, yeah. So now I'll play the video. So this is the National Grid Powerhouse, and as you can see, we made each and every one of our loads. All of our loads are powered by 2 different energy sources, the wall outlet source and a solar panel. So we have a resistive load right up here. That is a microwave that's powered by our solar panel source. And we have another resistive load powered by our wall outlet. We also have a capacitive load down here and an inductive fan. And while everything's going on, the system is constantly collecting data to be displayed on our touchscreen.
Thank you. Questions?
So you had an inductive, capacitive, and resistive load. Does that cover all the types? I guess does that cover all the models for the different consumer electronics in a home? Or are there others you didn't cover?
You want to answer? I'll go first and you finish. Okay. I'm sure that we didn't cover all of it, but our main requirement was to cover resistive, capacitive, and inductive, and our customer requirements was top priority. Okay.
Professor Ornstein, please.
Mr. Ornstein?
If you turn on all of your loads, just to put it in perspective of modeling a real house, what's the total power input into the house if the homeowner is not very energy conscientious and turns on everything?
So what's the total power in our house?
25 watts.
Our total power in our house is 25 watts.
And if we made the house human size, how much power would that scale to? Any idea?
I'm uncertain about this.
We didn't think about that.
Yeah, so we talked to our customer about this, and we're expecting to get data soon, just like to add it to our Raspberry Pi and just scale it up.
Okay.
Sam?
So you showed most of the testing setup in the video, and then you showed the shot of the final output at the end. So I just want to clarify: is the final output that graph of just power input? Or sorry, power output.
What do you mean? Like that's yeah.
That graph that you showed at the end.
Yeah,
That's the,
but and it also, if you're messing with the switches and stuff, it'll update in real time. So it's plotting while you're using it.
okay. So the main output is that plot.
Yeah.
All right, thank you, guys.